So let's restate the general asymptotics of the wave function. Which is the combination of the plane wave and their divergent cylindrical scattered wave. In principle, the Schrödinger equation allows for additional the third term, which asymptotically has the following shape. So the only difference is this minus sign in the exponent, and as you may guess, it represents the convergent to the scattering center cylindrical wave. Well, of course, since we're interested in the physical scattering event, we should fix all our constants in our wave function in such a way that this term disappears. Now let's recall the general solution of our Schrödinger equation, which is a general Bessel type decomposition. So now we understand that somehow this sum should be decomposed and merged into two main factors. The first of them will give us this plane wave term, and the second one will give us the scattered wave. So let's see how this comes about in the simplest case. We know that in the absence of the scattering center, there shouldn't be any scattered wave. So, and the wave function should be represented by the identical decomposition, but with alpha equal to 0, because alpha is proportional to our magnetic flux, and in the absence of magnetic flux is 0. So our decomposition will assume the form here, however, this modulus modulus in the index can be dropped. Why? Because for integer n, the Bessel function with index n and minus n, they are related to each other. And for example, if we write this sum for positive and negative n, the sum for negative n will look like g minus n e to in theta. But j minus n is actually negative 1 to n times jn. So and now we can denote this product an times negative n to n as an prime, and as a result, for negative n, the sum will have the same look as for positive n. So let's drop this modulus n in the index of the Bessel function. It actually simplifies things just a little bit. So, and as a result, we just rewrite the whole sum in the following manner. And of course, in the absence of scattering, it should be just a plane wave. Here I absorbed my Bessel function into this new coefficient Bn, which now contains all the dependence on the radius in my wave function. So now let's find out these Bn coefficients. Well, once you have a look at this, you clearly see that it is simple Fourier expansion of this function on the right-hand side. And Bn are just trivial Fourier coefficients. And they are easily found from the integral representation of their Fourier coefficient. So it's simply e to minus I kr cosine theta, the right-hand side, multiplied by their complex conjugate of their Fourier exponent, minus I n theta, and integrated over theta from 0 to 2 pi. And not surprisingly, this is a trivial integral representation for the Bessel function. hopefully you easily recognize it, up to some simple factor. This factor, you can easily convince yourself that it's true, or otherwise you can look up the supplementary materials to the lecture. So it's basically a function up to this negative I to n prefactor. And now we figure out what these coefficients a n actually are. They are just negative I to n. So, and what we get so far is the so-called cylindrical wave decomposition of the plane wave into these partial cylindrical waves. Right. So now let's actually track back how can we sum up this this series to get the correct plane wave. So let's move back in the opposite direction. So here is our full decomposition. The sum of over all n of negative I to n, jn of kr times e to I n theta. Why do we need it? Well, because once we trace how the different terms of these functions behave, we'll be able to reconstruct the same procedure for the more complicated problem with a scattering center, like a magnetic flux, which is our central problem. So let's see how it comes about. Well, first of all, the Bessel function is a non-elementary function. And to make sense of it, we need to use some kind of simplification. The first possible simplification, just to see how the whole thing works, is to check if this equality works for large values of r. Because for large values of r, we can substitute our Bessel function with its asymptotics. As you remember, the asymptotics of the Bessel function is a very simple one. It's the characteristic square root dependence times the cosine factor. What's so peculiar about this decomposition? We see that all the asymptotics expression which enter our function have the same prefactor, which is 1 over square root of r. So in the end, once we plug in this approximate expression for large values of r into our function, we get the following sum. It's the square root dependence. And the remaining sum is very simple. It's an elementary sum. In fact, it can be reduced to a simple geometrical sequence. And the interesting point that you can prove very easily that this sum yields identical 0. Which is, first of all, quite peculiar. But on the other hand, it's not so surprising, right? Because as we expect, in the absence of the scattering center, there shouldn't be any 1 over square root of r dependence, because this dependence is precisely the cylindrical wave, this scattered cylindrical wave dependence. So what we expect is that simple expression which represents the plane wave, but the plane wave somehow it's missing here. So how did it happen? How did we miss the initial plane wave in this decomposition? Well, the only possible answer is that somehow we can't use this asymptotic expression for our Bessel function. And why didn't it work? Well, obviously because the only reasonable explanation is that this asymptotic expression is only valid for not very large values of the index of the Bessel function. In particular, it works for n much smaller than kr squared. So the explanation is, it seems that the crucial terms in this sum are the sum with actually large values of n. And for these large values of n, we can't use this asymptotic expression. And the question is, so how can we indeed restore this plane wave from that kind of sum? And to do this, to restore it, we should use a different representation for our Bessel function. So the most suitable one is the integral representation in terms of a contour integral. So let's write it down. And the suitability of this expression lies in the fact that it's a contour integral. It's a closed loop integral around the origin in the complex plane of complex variable t. And to compute that kind of integrals, one sometimes can use residue theorem. And that thing makes all their calculations simpler. So let's continue on our next slide, and let's see how the whole procedure actually convolutes this sum into this plane wave.